Alright, hi everyone. Today we are going to take a look at negating our statements and what that means as far as the truth tables as well as our logical connectives. So first, we're going to negate each of our logical connectives and see what that looks like. So this is section 7.04. Negation. And our first logical connective is and. So if we negate P and Q, this actually negates both of the statements and then flips the and into an or. So we would say that this statement is, we use 3 lines here to indicate that this is logically equivalent to not P or not Q. And we'll take a look at this with our truth table and we'll actually prove that these statements are logically equivalent. Our second one is when we negate an or statement. So this is logically equivalent to not P and not Q. So these two are actually called De Morgan's laws. So it's a guy, De Morgan's his last name, and he kind of founded these two ideas that when we negate an and statement, we're negating both of the statements, and then we flip the and into an or, and then similarly for an or, it becomes an and statement. So again, we'll prove this with a truth table in a moment, but those two are pretty common principles that we'll use quite frequently throughout this course. Our third one is as if we just negate a negated statement already, and that just gives us back our original statement. Let me skip a line here. So 4 is if we negate a exclusive or, and this is actually logically equivalent to another logical connective, and that is the biconditional if and only if. So this one's actually pretty easy to remember because those two go hand in hand. So if I negate a if and only if statement, it becomes an exclusive or as well. So those ones are pretty easy to remember. If exclusive or and if and only if are always partnered with each other, they're exact opposites. And then lastly, we have our if-then statement. And the if-then statements, this one sometimes it's kind of hard to remember, but we will take a look at that in the truth table, so it'll make a little bit more sense. So this is logically equivalent to P and not Q. So again, we'll prove these in our truth tables. So let's go ahead and just take a look at the first proof of sorts here. This one will do proofs. By truth table. So let's go ahead and just start with the first one. So we have not P and Q, and we want to essentially prove that that is logically equivalent to not P or not Q. So a lot of us were having troubles with this yesterday. Please order your table in alphabetical order. So always start with P in your table and then Q. And then if we had R and S, keep going. So I know how many rows I'm going to have because it's based on my number of propositions. So I have 2 propositions here, so I'm going to have 2 squared. So the base is always 2, the exponent is the number of propositions. So then I'm going to do whatever's in parentheses, so P or Q. And then I'm going to do my final statement, not P and Q. And I'm trying to see, is this logically equivalent to not P or not Q? So that means I'm going to need a not P column, a not Q column, and then my final logical equivalence, not P or not Q. So I'm going to be focused on this column here and this column here. We want to see, are those logically equivalent to each other? So let's go ahead and get started with our truth table. So again, P is always, the first half is true, the second half is false. Q is a quarter true, a quarter false. So this one, since it's our last proposition, will just alternate. Then our and statement, so again, and is only true if both of them are true. So we have true, false, false, false. And then we're going to negate this column here. So let's go ahead and just negate all of that. So we have false, true, true, true. Then we have our negation of P and Q, so false, false, true, true, false, true, false, true. And so now we're going to connect these 2 columns with an or. So or is true if at least one of the statements are true. So the first one here is false. False or true gives us true. True or false gives us true. And then true or true also gives us true. So these columns here, these match up. So we've just proved that these statements are logically equivalent to each other. So now let's go ahead and do our second one. So the or, we want to say that not P or Q is logically equivalent to not P and not Q. So again, we start with our P, we start with our Q. We need 4 rows there. And then we can do the P or Q, the not P or Q, not P, not Q, and then not P and not Q. And, okay. So now, again, we just start the same way. So we're getting a lot of practice here with our truth tables, which, based on what we submitted yesterday, some of us need a little bit more practice, and that's okay. This is not something that's intuitive, but once you get the hang of it, it kind of just follows the same pattern every time. So P or Q, so that is when at least one of them is true. And then we can negate this whole column, so false, 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 true. And then we negate P, so false, false, true, true. And then not Q, false, true, false, true. And then we connect these 2 columns with an and. So again, and is only true if both statements are true. So we have false here, since those both are false, 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 and then last we have true. So again, these 2 columns are exactly the same. So we've just proved that these statements are logically equivalent to each other. So the next one's pretty easy. We want to prove that not P is logically equivalent to P. So not P, not P. So let's go ahead and just start. So P, not P, not P. So looking at this, we just have true, false, and then false, true. And then if I negate this column here, we can go ahead and see that that's going to be the same. So these two columns are the same, so those statements are logically equivalent. And that one's pretty easy to conceptualize. Not a lot of issues going on there. But let's go ahead and do 4 and 5 actually together, since the exclusive or and the if and only if are together. So we're going to do these in the same table. So 4 is not exclusive or is logically equivalent to this if and only if. And then number 5 is not if and only if for exclusive or. So we're just going to build this all in the same table so we don't have to make another table. So let's start with our P, Q, P exclusive or Q, not P exclusive or Q, P if and only if Q, and then not P if and only if Q. So we have true, true, false, false, and then true, false, true, false. So you can see, again, these are staying the same pattern. So we just go ahead every time. It's not going to be anything different. So let's go ahead and do our exclusive or. So exclusive or is going to be true if one of them is true but not both. False, true, false. Oh, excuse me. That one is true. False. So we have false, true, true, false. And then let's negate that. So true, false, false, true. And then we have the if and only if statement. So this is true if we have the same truthhood. So we have true, false, false, true. And as you can see, these columns are logically equivalent. So we have just proved the first statement here, the number 4. And then if I go ahead and negate this last column here, we would have false, true, true, false. And as we can see, that then these are exactly the same column. So we've just proved number 5, logical equivalence. All right, so we have one last one to do, and that is the if and only, or excuse me, the if then statement. So not P implies Q. So we said that this is logically equivalent to P and not Q. So to start, we should have our P and our Q like always. And we have, let's do P implies Q, not P implies Q. And then we have a not Q, and then P and not Q. So we have our true, true, false, false, true, false, true, false. And then implication is only false when we have true implies false. So this is true, false, true, true. And then negate that, we have false, true, false, false. And then a not Q, we have the alternating false, true, false, true. And then lastly, we just and our P and not Q. So true and false is false. True and true is true. False and false is false. And again, false and true is false. So as we can see, this column here is the same as this column here. So we have just proved our statements logically equivalent. All right, so we have some practice problems on negations. Please submit by 5 o'clock on Friday. It's Friday's lesson. And if you have any questions, I'll be on Zoom at 1 o'clock on Friday.